Inductor has an initial current flowing this way of 2 amps. The other way to say that is it has initial magnetic field flowing that way. So that's the initial condition. So then I can say, what is the voltage of the, or I can say, what is the current in the circuit, and the rate of change of the current at t equals to, so what's going to be the, let's say, let me give this a certain inductance, 15 millihenries over ohm. Let's say at 1.2 milliseconds. So what is the current and the rate of change of the current at t equals to 1.2 milliseconds, and the voltage of the resistor and the voltage of the inductor at t equals to 1.2 milliseconds. When is the energy of the inductor equal to twice the energy of the resistor? So that's a good one, kind of, because it's got an initial condition other than 0. So we could practice that, and then practice answering what the current is, what the rate of change of the current is, and then answering one of those energy type questions. Okay, so how would you proceed? So remember that the current in here, the current in the inductor, behaved like the charge of the capacitor. So it was some equation like this, right? E to the minus R, is it, RT over L plus VB over R. I think it was like that, but then A depended on what the initial condition is. I believe that's the equation, right? Because the R goes down there and is written as L over R. And that's the time constant, is L over R. Right? Yeah, that's the equation. So now in our condition, the current initial is negative 2 amps, right? So it's flowing this way. So now we can say I of 0 is negative 2. Now we can solve for what the A has to be. E to the minus, and then R is going to be the 30. Oh, I'm trying to solve for the A, so that would be the at t equals to 0. So actually t is 0, this would just be 1 plus, and then VB over R, and that would be VB over R, right? And then that would just be 2 over 3. So then A would be negative 2 minus 2 over 3. This 2 over 3 would go there. Negative 6, negative 8 over 3. So we're basically saying what condition does A have to satisfy so that when I put the initial current, I get negative 2. So then it's negative 8/3. So then once I have the current equation, negative 8/3 e to the minus, now I could put the R here, 30t over the L, which is the 15 millihenries. Plus the VB over R, 20 over 30. Okay, now I could put the 1.2 milliseconds here for the t, right? Okay, so I of 1.2 milliseconds, e to the minus, this one comes out 2, and this is 1.2, and then the milliseconds will cancel the millihenries. That's kind of why I made it milliseconds here. So millisecond cancels milli, so you're just left with 2 times 1.2 plus 2/3. Yeah, that tells you what the current is at any time. Okay. So negative 2.4 E, wait, E times 8 negative divided by 3 plus 2/3. Oh, so by that point, the current has already switched because the initial current is this way, but the battery is going to force the current to go that way. So it's already 0.425 amps. So it's flowing the other way. Okay, so then what else? Then the di dt at 1.2, so that's just simply the derivative of this function, right? Di dt, so then what would that be? Di dt, so negative 8/3. So essentially just this comes down and is negative 30 over 18 millihenry. No, is it 18? No, 15. 15 millihenry, 30, and then e to the minus 30t over 15 millihenry. And then the derivative of that is 0. Okay, so then the two negatives cancel. Right, and then it's going to be 310, 10 times 8, 80 over 15 milli, e to the minus, and now I could put the 1.2 milliseconds. So it's just going to be negative 2.4 again, e to the minus 2.4. Okay, then 18 millihenries, that's going to be actually pretty big. 18 divided by, since this is going to be 0.015, got to go back 3 spaces. Ooh, that's pretty high. Times 2.4 negative E equals 483.829, and that would be in units of amp per second. In other words, that's the rate at which the current is changing. The rate at which current is changing. Well, I guess that could be realistic. It's not that there's 483 amps, but the current is changing at that very high rate. Okay. Then the next thing is to just multiply VR and VL. So what would that be? VR should be whatever the current is times the resistance, right? Going this way, the current is flowing this way originally. So when you go this way, this is 2 amps. Okay, yeah, I get it. So this is 2 amps. You gain 20 volts. And then you gain another 2 times 30, 60 volts. And then you lose 80 volts. So originally, that's what the situation looks like. You gain 20, you gain 60 volts, then you lose 80, and then that's equal to 0. So 80 minus 80 is 0. Okay. So at that time, at 1.2 milliseconds, what's going to happen? You're going to get, the current has already switched on you. So then you're going to gain 20 volts. And now the current has switched to 0.425, right? And now you're going to lose 12.75 volts across the resistor. And therefore you should lose, let's see here, 728 minus 12.75, 7.25 volts across the inductor. Let's see. Times 1,000. 483 times 0.015. Oh, God dang it. I calculated this wrong. Oh, man. How did I get that? Oh, God. It was 7.25. God. 483.829 times 0.015. 7.25. There you have it. So then you have 20 volts minus 12.75 minus 7.25 volts, and that's equal to 0. So by that point, the inductor has switched, and it's working like that. 12 minus 12.75 minus 7.5, and the current has switched. Perfect. Okay, so when is the energy of the inductor is twice the energy of the resistor. Okay, and then with that, we are done. Energy of inductor, half Li squared. You want it to be twice the energy of the resistor. I can't use these equations, guys. I can't use these. These are assuming that my initial conditions are, okay, I have to continue this problem tomorrow because this is assuming that my initial condition of the inductor starts out at 0 current. Okay, can't use these. Cannot use these. So tomorrow I'll start with this. I had started using half Li squared, is twice energy of the resistor. And then I went to my formula sheet and I used I was beginning to use this equation for the energy of an inductor and the energy of the resistor. But the problem is these equations that are given on the formula sheet assume that the initial condition is that the current is 0. So there is nothing to start off with. So we need to kind of start fresh and say, okay, well, how would I derive an equation for the energy of the inductor and the energy of the resistor if the initial condition is not 2 amps? So then we would have to start with the current equation, I of t, negative 8/3 e to the minus 2 plus 2/3. Start out with that one. Now you square that. Right, so that's going to give me the general equation for the energy in the inductor. And then the energy of the resistor, well, what you do with resistors is you get their power equation first, then you integrate them. And then you derive an equation that might look like this, but with different initial conditions. So power of the resistor is I squared R. That's probably the quickest way to do it. So then the power is just going to be literally this equation. The resistance was what? 30 ohms. And then the I squared is just going to be this thing. Negative 8/3 e to the minus 2000 t plus 2/3 squared. So this is the power. So if I want to know how much energy has been dissipated in the resistor, then I say power is the rate of change of energy. I could factor out the 3, and then it'll just be a 9. It'll factor out as a 9, and I'll just have negative 8 e to the minus 2000 t plus 2. That's easier, right? And then the dt comes over here, and now you integrate it, and then you get an equation for the energy. And then this is 0 to some energy of the resistor, and then 0 to t. And we can integrate this. Let's see how we could just do expand this out. Energy of the resistor is going to be 30 over 9. And then when you square this out, you get what? Integral of this one squared is going to be 64 e to the minus 4,000 t, right? So that's literally how I got these equations, is by taking the general equation for the current and then integrating them. It looks kind of more complex than it has to look, you know, but when you do it with the numbers, it doesn't look as bad. So now 64 is the minus 4,000 minus the product of the two, double the product of the two. So 8 times 2 is 16 times 2, that's 32. E to the minus 2,000 t plus 4. And now we still got to integrate that. Right, so then you have energy of the resistor. 3 goes into here 10 times 3, 10 thirds. Right, yeah, 10 thirds. Now the integral of this is 64, and then the 4,000 comes out, negative 4,000. E to the minus 4,000 t, and then this one becomes what? Positive 32 over 2,000, because the negative makes the negative positive, right? And then you have e to the minus 2,000 t plus 4t. Then you evaluate from 0 to t. Then you put the t, which is just going to give you itself. So energy of the resistor as a function of time, 10 thirds. So negative 64 over 4,000 e to the minus 4,000 t, plus you put the t in there with just itself. Then you put the t there. Then you put the 0 here, which just gives you e to the 0, which is 1. So you say minus just this thing, 64 over negative 4,000. So that becomes a plus. So minus this one goes in here. Then you have minus 32 over 2,000. Right, so minus this guy, which is going to give you positive 64 over 4,000, minus e to the 0, which is going to give you 32 over 2,000. And then 0 goes into here, give you 0. Is that going to cancel? It looks like it, right? So 2, 2, 2, 2, 4,000, 4,000. Yeah, it canceled. Because in the general equation, it actually doesn't cancel. There's something here, 3L over something, but here I guess it canceled. Okay, so then 64, okay, that one's gone. Okay, so now I'm gonna impose the restriction or the condition that the energy of the inductor is twice the energy of the resistor. So then I'm going to set this equation, 1/2 0.015. The 9 can come out also again, over 9, negative 8 e to the minus 2,000 t plus 2 squared is equal to 2 times the energy of this guy. which is going to be 10/3, and then this thing. Yeah, I don't think I could factor out or make it any simpler. Okay, we probably just have to put that into Wolfram. Okay, so let's just go. Okay, let's see here. Okay, so 0.015 divided by 18 times -8 e to the power -2000x -8 e to the -2000x plus 2 to the power 2 is equal to 20 divided by 3 times -64 over 4,000 times e to the power -4000x plus 32 divided by 2000 times e to the power -2000x plus 4x. Whew. Now when we press enter, we can see it better. I mean, in this format, it's much easier to see. 0.018 over 18, -8 e to the minus 2 squared, 20 over 3, -64. X plus 4x. Okay, yeah, looks good. So there is an answer. It might have been that there was no answer, that that condition cannot be satisfied. But in this case, there is an answer. And it's very small. So we could say this is the time, 1, 2, 3, 0.0948 milliseconds. So we'll go 3 spaces and say 0.0948 milliseconds. At that time, that condition is satisfied. 0.0948 milliseconds. Okay, so you see what I did is I didn't use the general equation for that one. I used the one based on the current that I had derived. Right there, that's the answer, 0.0948 milliseconds. Cool.